Okay, so I guess let's start today's class. So hi everyone, welcome to CS 2105, Introduction to Computer Networks. This is tutorial 13, so I hope you are not in the wrong class. If you're in the wrong class, please go back to your original class. Okay, so a bit about myself. My name is Jason Christopher. You can call me Jason. I am currently a third year computer science student, and I enjoy swimming, reading, and coding, I guess. You have to do what you love, do what you enjoy, even if you don't like it. So I enjoy Indomie, and if you have any J-rock, J-pop recommendations, please let me know. I need to update my playlist. And obviously, I dislike the bell curve. So how about we go through with like one round of self-introductions, maybe your name, your year, your major, if you have any expectations for this module. And I mean, if you have any fun facts also, that's optional. Can start with you in the front.
Michael, year 3 information system. Not really much expectation.
Not really much expectations. Okay, you then. Sorry.
I'm Jermaine, year 4 computer science, and please don't fail me.
Yeah, that will be after the profs. But no worries, 5% attendance and participation, I'll handle that. Okay, then maybe.
Hi, I'm year 2
Comments.
nothing much.
Nothing much. Okay.
Hello, my name is Winston. I'm year 2 CS, and hopefully I don't die in small hill.
Okay.
Hi, I'm William, year 2 computer science. Expectation.
Nothing.
I'm Lucas.
Sorry?
Year 3 computer science.
Year 3 computer science. Thank you.
I'm Joshua, year 2 information security.
Nice to meet you.
Hi, I'm Mikhail, year 2 comp science. Hit average expectation.
Hey, nice to meet you, Mikhail.
I'm just from computer science and I don't really have an expectation.
Okay.
Year 3 the 5 is the expectation plus.
B plus. You can get much higher than B plus, I guess. Mm. No expectations. What's your name again? Oh, when do you? Okay.
My name is Tiffany and I'm computer science. I don't really have expectation.
Okay.
For year 3 data science, no idea.
Oh, everyone no expectations, one, you know. Keep up the energy. It's just the first tutorial, you know.
Year 4
You're sorry, what's your name? Cheng Hong.
Hi, I'm Julia, year 3 CS. I heard this module was like quite low in
Mm. Okay. Nice expectation. Okay.
I'm year 3 Mac Eng. I just want to pass more.
Chen Xun, okay. Okay, nice to meet everyone. So I guess we have quite a diverse range of students here from CS, IS, InfoSec, Data Science, and Mac Eng. Wow, that is quite a diverse range. So I hope that, I hope that y'all can try to benefit from the tutorial sessions also. So in any case that if you have any feedback on like what I can improve, can also let me know later lah. Okay, so if you haven't joined the Telegram group, please join. I suppose most of you have joined already, although we have 22 students in the class. So I guess if you haven't, can scan the QR code. I'll leave this for another 5 seconds, I guess. So any announcements related to the tutorials, I will post it here. Sometimes some reminders about assignments, if I think that not much have submitted, I will also post it here lah. Okay. So here attendance and participation is graded and it will be a total of 5%. As for the weightage between how much is allocated for attendance, how much is allocated for participation, that is actually currently ongoing with discussion with the lecturers. However, I will of course take note on how many questions you answered, how many answers, and also whether you actually attend to the classes lah. So later on, if your attendance has not been recorded, can also let me know. I will share my sheet that I use for attendance. So this is very important. Please place your name record at all times because I am quite bad at facial recognition. That's why I took computer vision module last sem, although it didn't help me at all. So please place it at all times. Last semester, I felt that there's like one person who might have sneaked in my class, then I don't know the person actually sneaked in lah. So please put this at all times lah, so I know who you are. Okay. At any point in time, if you want to contact me, please contact me through my email or through my Telegram. Prefer Telegram, but of course I also open email quite fast. Also, I am open to any consultation slots. If you have any questions regarding the module, you feel like you want to book a consultation slot with me, then please scan the QR code here, or you can also use the Calendly link to see my schedule. Okay, and of course, if you have any feedback at any time, I will be opening this form about once a week. So please feel free to write any feedback you want on how I can improve, since I'll be your tutor for about 10 weeks. Okay, so that's quite a long time. Any questions so far? Questions? No? Okay. If no questions, then we will start the tutorial today. The first lecture introduces you to everything about networks. Okay, when we say networks, usually we will talk about how to actually manage the delays and how do we actually transfer packets from one point to another. That is why we will discuss about packet switching. But before that, we will talk a bit about what a packet is. A packet is actually a fundamental unit of data. It is not 1 byte, it is not 1 megabyte, but it's just like 1 unit of data. This 1 unit of data is actually quite small, such that if you have a large file, you will want to try to split it down into small files that is easy to be sent. So whenever you send items, it will be 1 packet by 1 packet. Now, there are 4 kinds of delays in end-to-end delay. Anyone can recall what these 4 kinds of delays are? Propagation, transmission, queuing, and processing. Okay, so there is a processing delay, queuing delay, transmission delay, propagation delay. What are these? Or rather, what is a transmission delay? Okay, so I will give you a very simple analogy here. Suppose that here you are an orientation group leader. You handle like say 200 people within your OG. That's not an OG, it's more like an orientation program already. So you handle 200 people, this is your computing OG, but in front of you, there happens to be someone from science OG, for example. Both of you want to go to Com3. Okay? Now, one bus comes every 5 minutes. And this bus, you know when NUS updates their bus is actually quite small, right? You don't actually get inside. So one bus, for example, we assume they can hold about 50 people. Then you want to move from U-Town to Com3. Now, before you actually board the bus, the other OG who is in front, they should be able to board the bus first, right? Okay, so they will board the bus, go in. You have to wait until the next bus when you can try to board, but you have 200 people. The bus can only hold 50 people per 5 minutes. So 50 people will go in first, then you have to wait for the next bus again. Now, once you boarded the bus, it needs time to move from U-Town bus stop to Com3 bus stop. Then you move. Okay? So this is actually the 4 delays in action here. When you wait for the other OG to board, that is your queuing delay. You are currently this 1 packet. In front of you, you have like 10,000 packets. These 10,000 should be sent first. So that is your queuing delay. Once you actually reach this point, say for example, as an OG, you want to ensure that all your members are there. You don't want any members to be left out. You do a head count. Then that is a processing delay before you actually board the bus. But 200 people, each bus only holds 50 people. 1 bus comes at 5 minutes at a time. So you have to wait at least 4 times 5 minutes just for getting the bus right. Okay? So boarding the bus, waiting the bus, there is transmission delay without moving. It's just to get into the bus. Until the bus moves, then that is your travel time, which is your propagation delay. So transmission time is the time to push you into the network. Propagation is actually when you move from A to B. Okay, that is the 4 delays here. Any questions? Yeah. So say if you want to send just 1 bit of data, from NUS to NTU, the time it takes from one point to another, that is your propagation delay. Now we want to see what is the formula to count propagation delay. So question 1, suppose that you have two holes separated by m meters apart, and we suppose that the propagation speed, the speed that you travel across the link, is s meters per second. What is the propagation delay in terms of m and s? Anyone? M divided by s. Yeah, that is correct. So similar to the speed problem here, in physics, you have distance, you have time. Speed is equal to your distance divided by time. Okay? Thus, your propagation delay is just m by s. Any questions? No? Okay. Now, say you want to send, instead of 1 bit, you want to send 10 megabits of data. However, your link cannot hold 10 megabits at a time. So your link here, for example, they can only send like 1 byte per second, something like that. Then that is when you have to send them in small chunks to accommodate the bandwidth of the link. Okay? The amount of data that can be transferred at one time, that is called your transmission rate. Okay? The bandwidth of the whole link. So the time that, the delay that is caused to actually push this data into the network, not moving it, just pushing it into the network, that is called your transmission delay. Because your network only can contain 1 byte, but you have 10 megabytes. So that's a bottleneck here. Actually push it inside, that is your transmission delay. So now suppose that you want to send a packet that has size L bits. Then the link here is only one single link of rate R bits per second. We want to determine the transmission time of the packet, which is your D-trans. What is the formula for D-trans? L over R. That's correct. So you can imagine it like, for example, you have one large pitcher of water, right? It's L liters. You have a small tap that can only put like R liter per second. How long does it take to empty out the whole pitcher? That's basically your L over R. So transmission delay is equal to your size of packet divided by the transmission rate. Okay? Any questions? Usually if it's bytes, we write bytes. But of course, if it's capital B, then it's bytes, yes. But for the module, to actually like distinguish between whether it's bytes or bits, we actually write bytes. But for small b, it's always bits. Okay? Any questions? Okay. Now, back to this example. Say, for example, if you want to process the data before transmission, then that is your processing delay. If your current packet here, in front of you there are another packets, you have to wait for the other packets to go first, then that is your queuing delay. So these are all the 4 types of delays. So for processing delay and queuing delay, these two are not actually considered that much in the module in terms of their calculation. However, they might pop out as like, for example, suppose queuing delay is how much, then you have to account it for the end-to-end delay, which we will see in the next few questions. Okay, any questions? Now, ignoring processing and queuing delays, can we calculate an expression to obtain the end-to-end delay? Anyone? You can raise your hand. Yeah, you are, can't see the name. A bit too far. What's your name? Can mention? Chan Yang, okay.
So we take the previous 2 formulas from previous 2 parts and add them together.
Okay, yeah. So just add the transmission delay and the propagation delay, then you should get the end-to-end delay ready. Okay? Any questions? Okay. Now, say for example, A begins to transmit the packet at time t equals 0. When the time is equal to the transmission delay, where is the last bit of the packet? Okay, maybe we can try to visualize this, right? Say for example, I have like my packet's only 8 bits. Then say transmission time is 2 bits per second. Okay? So we start at t equals 0. T equals 1, t equals 0.5, 1, 1.52, 2.53, until when my t equals 4, that is my transmission delay, right? 8 bits over 2 bits per second, so 4 seconds. At time t equals 4, you will see that your last bit here is just about to leave your host. Okay? So at t equals your transmission delay, the last bit is actually they just left the host. Okay? Then that is when we actually stop the transmission delay. Any questions? No? Okay. Now, this one is fun. We know transmission delay, we know propagation delay. What happens when the propagation delay is larger than your transmission delay? When t is equal to the transmission delay, where is the first bit of the packet? Still on the way, exactly. Okay? So say here, when t equals your d trans, the last bit just left. However, since your propagation delay is much larger than the transmission delay, your first bit here, it is still actually part of the link. It hasn't reached B. Okay? Now, if the propagation delay is less than the transmission delay, then what happens? It's already reached B, of course. Okay? So you can think of it this way. When transmission delay is larger, then of course, the first bit already arrives at the destination. Okay? Same goes if, for example, if you wait the bus, if the bus is 30 minutes once, if the first bus left, then when the next bus comes, the first bus is already at COM 3 lah. Okay? Something like that. Any questions? Okay. Now, this one is more messy. So suppose that we have S is equal to 2.5 times 10 raised to 8, L equals 120 bits, R equals to 56 kilobit per second. So S itself is the propagation speed, L is the packet size, and R is the transmission rate. We want to find the certain distance, how long the link should be, so that the propagation delay is equal to your transmission delay. Anyone has an answer for this? It's a large number, I think. 5, 3?
35714.
Okay, yeah. I think that should be correct. So, suppose we do this. First thing is we just put the equation first. You want your d propagation is equal to your d trans. Then you put the formula. Propagation delay is the length of the link divided by the propagation speed. Then for your transmission delay is equal to the file size, the packet size, divided by the link rate or the transmission rate. Just plug in the numbers, you will see that your m is equal to this 120 bits multiplied by the propagation speed divided by the transmission rate. Then you will get this 535,714.29. Okay? Any questions? No? Okay. Now, that is for question 1. Now we move on to question 2. So question 2, suppose that a packet switch, they receive a packet. We want to determine the outbound link to which the packet should be forwarded. So when the packet arrives, one other packet is halfway done being transmitted on this outbound link. 4 other packets are waiting to be transmitted. Something like this. Say this is your packet here. In front of you, there are 4 packets. And then there's also one packet that is already halfway being sent. Okay? The question is, suppose that if you assume that all packets are 1,500 bytes and the link rate is 2 megabit per second, what is the queuing delay of the packet? Anyone? Yeah. 27 ms. How did you get 27 ms? Like this?
Yeah, divide by 2. Then the rest you times 4.
Mm.
So everything. Then after that, you times 8, you convert it to bits. Then after that, you divide by the link.
Yeah, I think that should be correct. So maybe let's see. So this whole thing, you have 4 packets. Then there's a 0.5 packet here that is still waiting to be sent up. Okay, so that will account to 4.5 times 1,500 bytes. That is 6,750 bytes. However, you will see this note again and again every single week. I will mention this. Bytes and bits are different. Okay, so whenever you see bytes, but your propagation speed is in, your transmission rate is in bits, make sure to convert them to bits. Okay, remember this. Bytes and bits are very important. This one is always a trick question in every midterm and finals. Okay, So convert the bytes to bits, then you will know that the amount of files still in queue that is 54,000 bits. Now, the queuing delay is, of course, you want to wait for these 4.5 packets in front of you to actually be sent. Okay? So, there's still 54,000 bits that needs to be transmitted. Then the queuing delay is simply this thing, how long does it take for 54,000 bits to be transmitted? Then just divide this by the transmission rate, you will get 27 milliseconds. Okay? That's the queuing delay. Thanks, Lyndon. Any questions? Okay. Wait. Yeah. If no questions, now, this one might be a bit tougher. So suppose that just now we have the numbers, right? The numbers of how much each size of the packet is, what's the transmission rate, and how much of the current packet has been sent. Now suppose that we change all the numbers into actually just algebra lah. Suppose that you have each packet of length L, then you have a transmission rate of R, then you have X bits of the currently transmitted packet that has already been in the link. Then we have N packets that are already in the queue. So what is the queuing delay? N times L plus X divided by R. Probably there's something missing there lah. There might be something missing. It's not plus X. N times L plus. Yeah, I think that should be correct, yes. Because the X here is already transmitted, right? So the one that needs to be transmitted is this thing, which is your L minus X. Yeah, but the rest should be correct. So thank you, Alina and Cheng Hong. Okay. Yep. So you have N files in front of you, and this one that is currently being transmitted. X bits has already been sent, so this one we don't have to account for the queuing delay. The one that we have to account for is this part. The current file, L bits. X bits has already been transmitted, so the remaining one that we need to transmit is L minus X. Okay? N files is NL plus this L minus X. This is equivalent to how many bits that we need to transmit. Divide this by the transmission rate, then you should get NL plus L minus X over R. Okay? Any questions? Questions? No? Okay. I think we still have quite a number of questions left. For those who haven't participated, please let me know. Please answer the questions. I'm marking your how much you actually participate lah. Okay. So, the next question here. In modern packet switching networks, we have something called a message segmentation. That means if you have like say one large file, we don't actually send this large file as one packet lah. We try to cut it down into smaller packets. Okay? That's your message segmentation here. So consider a message that is 8 times 10 raised to 6 bits long. That's to be sent from the source to destination. We suppose that each link, so this link, each of them are 2 megabit per second. We ignore the propagation delay, ignore queuing delay, and ignore processing delay. So we want to send this message from the source to destination without message segmentation. How long does it take? 4 seconds. How do you get 4 seconds? 8 megabits divided by 2 megabits per second. That is for one link. Now the question is, if you send something, for example, you send an 8 megabits here, right? Does it directly go here directly? So if you send say the first bit, does it directly go all the way to the end? No. If you put 4 seconds, then you assume that everything here is just pass by until the end. Then that's 4 seconds.
Each link can be switched.
Oh, first switch. Oh, sorry. Yeah, first switch is 4 seconds. Yes, thank you. Yeah, so in this case here, there's 4 seconds. Sorry. Yeah, first switch is 4 seconds. Yes, that's correct. Sorry for that. Okay, now what is the total time to move the message from source to destination? 12. Why is it 12?
Store and forward.
Exactly, because it is store and forward here. Okay, so store and forward, the switch needs to receive the entire message before it can start passing to switch 2. Okay? So say if I have, let me simplify this into say 4 bits. Okay? So from the host to switch 1, the first bit will have to be maintained in the switch first before it can move on to the second one. So once the last bit of the packet arrives, then the first bit can start moving to the next one. Okay? Move again, that's another 4 seconds. Until you move to the last one, that's also another 4 seconds. So in total, this whole thing is 4 plus 4 plus 4, which is 12 seconds. Okay? This is because of the store and forward mechanism. If there is no store and forward, then the first bit can just flow all the way to the end. But because of the store and forward, block here, until the last bit arrives, then you can start moving. Okay? Now we suppose that the message here is segmented into 800 packets. Each packet is 10,000 bits long. How long does it take to move the first packet from the host to the first switch? Five milliseconds? Yeah. So this is simply just a transmission delay of one packet. That is 10,000 bits divided by 2 megabit per second, then that's 5 milliseconds. Okay? Thank you. You are Tiffany. Okay. Now, when the first packet is being sent from the first switch to the second switch, the second packet is being sent from the source to the first switch. Okay? So something like when the first packet is from here going here, then the second packet is from here going here. Okay? At what time will the second packet be fully received at the first switch? 10 milliseconds, that's correct. So, starting from 0, first packet is already in the first switch. Now, when the first packet starts moving to the second switch, second packet will start. Until when the second packet arrives at the first switch, that is 10 milliseconds. Okay, 5 plus 5. Questions? With that being said, how long does it take to move the file from the source host to the destination host when message segmentation is used? 4.01 seconds. How did you get 4.01?
First packet will take 15 milliseconds. Then subsequently, once the queue get loaded up, each of the subsequent packet will only take will be right after you. So the other 709 packet is 3,995 milliseconds. 3995.
How did you get 395?
So subsequently, after the first packet, the second packet will be right next after the first packet. So each of them will only have 5 milliseconds. So you add up the first and the other 700 and you will get 4.01 seconds.
So this one plus the 15 milliseconds, then that would be 4010 ms, which is 4.01.
Yes.
Okay. Yeah, that is correct here. What's your name?
Jason.
Oh, the other Jason. Okay. Wait. Oh, okay. Okay, yeah, this is correct. Everyone got what he said. So the logic here is, if you try to trace again this simulation, once 15 milliseconds arrives, the first packet will already arrive at the destination. You continue another 5 milliseconds, then the second packet will arrive. Okay? So once the first packet arrives, every single packet here just need to wait 5 milliseconds, they will come to the destination. Another 5 milliseconds, the next packet will arrive. Okay? So in total, 15 milliseconds is for the first packet. Next few packets will come every 5 milliseconds. So you have 799 packets remaining, times 5 plus 15. That is your 4010 milliseconds. Okay? Or another way to think of it, right? If you only have one single packet, from the source to the first switch, that is 5 milliseconds, all the way next, until it reaches the destination, this last point here is 15 milliseconds. If you have a second packet, just have to add something below it. Okay? Then now this will be 15 milliseconds plus 5 milliseconds. Third packet onwards, until the 800 packet, this will be at 4010 milliseconds if you want to try to visualize this. So the time it takes here is, this is your 15 milliseconds, this is your 799 times 5. Or you can also think of it, right? This part here, the one before the first bit of the first packet arrives, that is your 10 milliseconds. This is your 800 times 5. So 4000 plus 10. Okay, that's another way to think of it. Any questions? Yeah. This one is actually a crucial question, because later on when we start to account for propagation delay, things might get a bit complicated lah. So try to understand this example first. Yeah. So we can see that if we use message segmentation, your 4.01 second is actually significantly less than sending a big file as one message. Yeah, so now we just need to wait 4.01 seconds instead of sending the huge file, that is your 12 seconds. Okay? Any questions so far? Now, in addition to reducing delay, why do we use message segmentation? Anyone? Those who haven't spoken? More reliable? What's your name? Hengxun. More reliable, okay. Why is it more reliable? Actually, reliability does not is not really correlated with whether you apply segmentation or not. That's more of the network itself. But of course, compared to say sending a huge file, right? One bit corrupt, you have to resend the whole entire file. If you split it down, you just need to resend that small thing, right? Yeah, so in a sense, not really saying that it's more reliable, but in a sense more efficient when you try to send it. Yeah.
If you split up the message, can't you send it to multiple devices, like in parts, so like if the network's like distributed?
Yes, that might be working. Yes, it's similar to BitTorrent later on, peer-to-peer communication. So if you, I think later on in the later tutorials we'll also discuss about BitTorrent. BitTorrent is when you use peer-to-peer communication, your whole file is actually split into different servers, different hosts. So when you want to receive one file, it's actually receiving from multiple computers. So kind of a distributed one. So yeah, that's a valid answer too. Anyone else? But that one is actually more into, not really in the segmentation part, but more into when you split into smaller packets, I guess. Yeah.
Reduce congestion on the network.
Reduce congestion? How is it so?
Because you won't occupy one line. All the lines will be open to send more. Like you won't have one line just reserved for that signal.
Yeah. Okay, yeah, that's correct. Anyone else?
Yeah. So basically, right, if you send one large file, right, then it will just talk a low file. So like if you break it up into packets, then the smaller packets behind can still use.
Yeah, that is correct. So I think this will follow on top of the congestion one, right? The congestion is actually, I think congestion control will be discussed in the transport layer also. But actually, the blocking of the file is actually what we concern more, especially if you see like from a larger perspective, right? Then when you have one huge file to be sent, the other files, they can't actually be sent. They have to wait for this huge entire file to be sent first. So they can't interleave together.
Actually, I really talk about UDP and TCP. So like streaming media, right, like live media, like having segmentation in the file, video file being sent is much preferred over TCP. So you have, like, let's say a drop frame, it doesn't really matter in like, the video context. And having TCP to stream like live media would be overall slower. Would that be?
Yeah, I think someone has done their homework. So actually UDP and TCP will be covered in 2 more weeks for the tutorials. But yeah, tutorials are 2 weeks after the lecture usually. So yeah, actually it will be covered in the next few tutorials. But I suppose the difference of UDP and TCP is it's a trade-off between speed and reliability. Not really into whether we want to segment the message or not. Yeah. Because say for example if I can also use message segmentation with TCP, right? Of course. Say one huge file I can just put it in smallly. I want to ensure that all the packets actually arrive. But for both of these can be applied to both UDP and TCP. Just depends on how you want, whether you want speed or whether you want reliability. That's a UDP TCP trade-off. Okay, let's discuss here. So just now I think, so just someone mentioned about having to, it's more like efficient in a sense, right? Yeah, the one that you mentioned just now. So you of course have encountered this. You download like this huge 5 GB file, right? Suddenly when something is wrong, you have to re-download the whole thing. Okay? If you use message segmentation, this would likely not occur. Because without message segmentation, if there are bit errors, you have to resend the whole thing. With message segmentation, when you split into smaller chunks, just have to resend each of the small chunk that is erroneous lah. Okay. Then without message segmentation, then you have huge packets. The routers have to accommodate to this also. So something like, say if you want to send a video, if I use message segmentation, this video will be split into smaller parts, right? Say video part 1, then suddenly this small humble Google Docs will come in, can be sent together before the next few videos come. Okay? Compared to if you don't use message segmentation, if you don't know what this video is, this is the video. It's a 3-hour long movie. The humble Google Docs will have to wait for this huge movie to be sent first, before it can be sent. Okay? So that is some ideas of using message segmentation. However, there are some pros and cons also. So anyone can tell me why, in what cases should we not use message segmentation? Or rather like, any cons of using message segmentation?
I think you got more packets, so you have more packet headers. It's like a lot of wasted memory. Like a lot of packet overhead.
Yeah. One thing is overhead, that is correct. What's your name again? Joshua, okay. Joshua, yeah. I dislike this venue, hard to see the names. Yeah. Okay. Yeah, that is a valid point. When you have like different smaller packets, each packet will of course contain their own data, right? Packet is not just purely the data itself. They will contain other things called the metadata or the packet headers later on we will see. This will contain information about the packet. If you split them into say just one bit per packet, it might be possible that the entire packet headers can be like say 8 bytes for example, just to send that one single bit of data. So in the end, it will be lots and lots of packet overhead. Any other drawbacks?
I think you need to order the packets for the destination.
Yeah, packet reordering will happen because you will see later on that not always the packets will come in the correct order. Especially later on in the routing protocols, they can actually go on different routes. So it might be possible that say the part 2 item comes before part 1, so additional logic must be handled to handle these out of order packets. That's correct. Okay, so first one, of course it has to be put in sequence at the destination, then it might also incur greater overhead. Okay, any questions on this? If not, we move on to question 4. Question 4, we have n devices to be connected. Then there can either be 0 or 1 link between any 2 devices. So what is the minimum number of links needed to connect all devices? n-1. How do you connect n-1? What kind of arrangement would that be? A tree, okay. Yeah, a tree makes sense. Any other ideas how we can make n-1 links? Circle. Is circle n-1? I think circle is n links. Circle is n.
Minus the last one.
Minus the last one. So, yeah, say if I have 5 at this side, if I make a circle, then 1, 2, 3, 4, 5, that's 5. So something like here. Yeah. Then this one is just a line.
Just one line.
Yeah, this one makes sense also. That's what we call, I think this is what we call the bus topology. Just one line. So there's a tree topology, there's a bus topology. Anything else? M1? Kristen? Yeah. So one dot, you connect this, right? This will be n minus 1. This will be n links, I think.
There's one in.
Oh, I think the whole
Oh, the whole okay, yeah.
one line.
Yes, that is, yeah, that's n minus 1, yes. This is what we call the star topology. Okay? Yeah. So n minus 1 link is sufficient. You can do a star topology like this. Yeah, 7 devices, 6 links. The middle one, anyone knows what this is? Switch. Actually, this one is what we call a hub, usually. Okay? Switch also makes sense for this. Then we have a chain topology. Or sometimes you also call this a bus topology. You have 6 devices, 5 links, just connect everything here. And as what Michael mentioned, this is your tree topology. Okay? Why is tree topology correct? Because I think you have learned in 2040s that if a tree is connected, the number of edges is n minus 1. So if you have n nodes here, they are connected as a tree, then you are guaranteed to have n minus 1 edges. Okay? Now, we discussed the minimum, which is n minus 1. What is the maximum?
N squared.
N squared? Might not be right. Okay, maybe. N squared minus n over 2. How did you get n squared minus n over 2?
And after that you do the summation of arithmetic sequence.
Mm.
And,
Yeah, yeah, that's correct. So you can think of it like, say, for example, you have these 5 items, right? The way you can do this is every single node will connect to every single thing, right? So every node will have n minus 1 links. Okay? Then another one here that will also have 1, 2, 3, 4, n minus 1 links, n minus 1, n minus 1, n minus 1. But wait, a link between here and here is the same thing as the link between here and here, right? So then you have to halve all these numbers. So you have n nodes, each of them n minus 1 links, but you have to account for the reflective property. So divide this by 2. Or you can do the arithmetic sequence. This is n minus 1. Since this already been covered by the link, this will be n minus 2, n minus 3, n minus 4, which is just this one link. Then this one doesn't have to be connected really. So there'll be n plus n minus 1, n minus 2, n minus 3, n minus 4, all the way to just 1. Okay? There are 3 ways also to solve this. The other way is you can just use combinations. N different nodes, choose 2. There's n choose 2. Okay? Any questions? Yeah, so this kind of topology is what we call the mesh topology. Okay? It looks like some kind of a cult here. But anyways, this is your n times n minus 1 over 2. It forms a complete graph, in case you are wondering how this works. Now, we've seen that there's one that uses extremely large amounts of links. The other one uses a very minimal amount of links. What are the pros and cons?
One lane fails, right? There's another pathway to like the same between like between device A and B, there's another pathway.
So if you have more links like the mesh one just now, there's a reliable pathway. What about the n minus 1 links, the very minimal one? What happens? Those haven't spoken? Moonhui, Winston, Xavier, Amos.
If you use the normal like the chain one, right? Let's say if one fail, then you don't know which one.
Exactly. So, say if you use the minimal ones, okay? If you use the minimal ones, what happens if these 2 links break? Can they communicate? Can this communicate with this? No, right? And that's actually what happened before. If you have read the news, there was one time that sharks actually ate the cable between 2 oceans. So they cannot connect. Okay? So this is actually a true problem. Then you have to put some backup on that. So yeah. First one is, of course, you have like just simple items. These are cheaper. Okay? Then any other pros for minimal ones?
In terms of management and setup, it's a very easy process.
Yeah, that is correct. Just have to connect between one and another, right? Don't have to maintain 4, 5, 100 different hosts. So yeah, it's easier. Anything else? Okay. So the problem here is, of course, it's prone to a single point of failure. And if you have, like, say, a chain topology just now, if you happen to be at the last end, and you will also be like a bit sway, a bit unlucky to get at the last end also, you have to travel between, say, for example, 1 million nodes just to send the data to the last person. Okay? So that's quite normal. Now, free participation points for those who haven't spoken. What about you have the B item? What is the pros and cons? You can just revert everything. Yeah, I most.
To set up, plus you need to like set up all the different networks, like routing and stuff.
Difficult to set up, yes? More efficient? How is it more efficient? Okay, shorter links, so faster to send data. Anything else? Exactly, but it's expensive. Okay, so it's faster. There's still backup, reliability, but money is a concern. Okay? Any questions?
Can I ask is the n minus 1 considered less secure? Because there are so many like points where people can listen in.
Which one?
The n minus 1 link.
N minus one links.
Let's say you want to transmit a message from A to B, And it's like okay, A to C, then there's B in the middle, right? So like B will technically have access to your message before you just read. Then if you compare it, you connect directly from A to C. Then there won't be a middle, right?
Yes, you have a point there. You do have a point there, but you can also argue that in that case, one can also randomly pass through like any separate route lah. So it's not really like guaranteed to be that one single link. Compared to, for example, if you just have like say a star topology.
Yeah.
If I'm the middleman, I'll just stay in the hub. Then I know everything really. Right?
Yeah.
If I have mesh topology, I can, for example, today I go through this way, tomorrow I go to another way, then that introduces randomization. So there's still lots and lots of consideration. The solution to that, encryption, better security protocols. Okay. Yeah. So with that, then that's the end of this tutorial. So let me just scan through the attendances quite a bit in case I haven't marked. Is Nathan here or Nathan is not here? Xia Ao? Is Xia Ao here? No? Xavier is here, right? Okay. Okay, then I guess all of you should have been marked attendance for the rest. So that's all. Thank you for coming. Assignment 0 has been released and will be due next week, I think. So please don't forget to do this. Start early, start learning Python early. This will be helpful for the rest assignments. Then that will be it for today. Thank you. Oh, sure.